Hello everyone, welcome back to Under the Apple Tree, and today we're going to be going over some optimization problems. Optimization problems can be often tricky because you have to use multiple equations for a shape, surface area, volume, area, perimeter, whatever. And so that often confuses people, which one do I take the derivative of, which one do I solve for? It can be a little bit messy, so let's just jump right in and see if I can help you out. So if a cylindrical tin can with an open top is designed to hold 30 cubic centimeters, what circumference will minimize the amount of tin needed? Okay, so this is a really good problem. Applications for the real world are very obvious. You don't want to use more tin than you have to. If you're making the same volume, this is a good question. So we know volume is equal to 30 cubic centimeters. Okay, what's the volume of a cylinder? Pi r squared h. Okay, well, so if we look at this equation, we have two variables. And two variables, we can't do anything with this. So let's go ahead and solve for one in terms of the other. And the reason we're going to do this is because we're going to have to plug this into a surface area equation. And take the derivative of surface area and then find which radius will minimize your tin. So since we're given volume, we're not going to take the derivative of volume. That's a pretty good rule of thumb. Not given volume, we use this equation to find variable values. We're not going to take the derivative or anything like that. Okay, so let's plug in our 30 equals pi r squared h. And I'm just going to solve for h. It doesn't matter which one you solve for. In this case, it does actually, because circumference is 2 pi r. And so we want to find height in terms of radius, plug that into surface area so we can get a surface area in terms of only radii, and then we'll plug that radius into this circumference. That's the game plan. See if it works out. Okay, so we're going to divide pi r squared over, and this is what this is our relationship between our height and our radius. Okay, now let's do surface area. So for this, you have to know the surface area of a cylinder, and hopefully your professor or teacher gives it to you on an exam, because it's kind of brutal to remember. 2 pi rh plus 2 pi r squared. Okay. Now this equation has some explaining to do. So this 2 pi rh describes this part of it, and this part describes the circular parts. Now we have to pay super close attention because look, one of the parts is open on the can. There's no top circle, if you will. So what that means is this value, the blue value, has to be cut in half because there's only one. So S equals 2 pi RH. That's just going to be pi r squared. That's a plus sign, so 2 pi RH plus pi r squared. Just in case you didn't get that or it doesn't make sense, this blue part that I underlined corresponds to the surface area of the circles of the cylinder, and since one is open, we have to do half of this value. Alright, so now let's just get on to solving for our radius. So first thing we can do is plug in our height values here. S is equal to 2 pi r times our height. Our height is 30 pi r squared plus pi r squared. So now everything is in terms of radius, which is great. It's what we want. We can do some canceling. Our pi's will cancel. One of the r's will cancel here. And so let's do some simplifying. Surface area will now be equal to 60 over r. And then this last term has not changed yet, plus pi r squared. Okay, so this is an optimization problem. Minimizing or maximizing, it doesn't matter. What matters is we want to find the optimal point. And when you want an optimal point, a maximum or a minimum, the derivative is 0 at that point. So let's take the derivative of this function and set it to 0. Because when the derivative is 0, that's how you know it's a maximum or a minimum. So SR prime, the derivative of 60 over r squared is negative 60 over r squared. I'm assuming you're pretty good at derivatives by now, and you know how to take this derivative. Just put the r on top, make it a r to the negative 1, multiply everything by negative 1, and then subtract 1 from the exponent. You get negative 60r to the negative 2, and then I just move the r2 to the denominator. And then derivative of pi r squared is 2 pi r. Okay, and now we want to set it to 0 because that's when it'll be at an optimal point. 0 equals negative 60 over r squared plus 2 pi r. Now we solve for r. I think I'm just going to skip a lot of the algebra because, what's the point? But I'll say what I would do. So I would add over this 60 over r squared, and then I would multiply everything by r squared. So then on the left side we would have 60, on the right side we would have 2 pi r cubed. And then we could divide we would divide the 2 pi, and then we would be left with r cubed is equal to 30 over pi. And then we take the cube root. R is equal to the cube root 30 over pi. So we still haven't answered our question yet. We still don't know the circumference, but we know the radius when the amount of tin is minimized and our volume is the same. So we just plug it in over here at our circumference. So this problem you actually had to use 3 equations. And this is about as dirty as it'll get, to be honest. It doesn't get much worse than this for optimization. I just wanted to show a really tricky one, so it's only easier after this point, Let's redo that 30, not 36, it's 30. Okay. The circumference at which you will minimize the amount of tin needed is 2 pi times the cube root of 30 over pi. I would say what makes this one so tricky is the open top. And you have to adjust your surface area equation accordingly. And then you have to choose to get h in terms of r. That's also tricky. You have to get h in terms of r. If you do r in terms of h, you'll get a value here, h equals blah blah blah, and then you won't be able to plug it into your circumference. Okay. An ice skating rink consists of a rectangle with a semicircle at each end. Find the maximum area of the rectangle in terms of p, if the perimeter of the ice skating rink is fixed at p feet. Okay, so for this one, we're given 3 shapes, and we're not given any values for the area except for p. We don't really know what that means. We're just going to call the rectangle legs x, and since we have a semicircle, this distance would be r, this distance would also be r. Okay, and same with this side too, but I'm not going to write it again. You get the idea. Okay, so we want perimeter and we want to maximize area. So that means we're going to be taking the derivative of the area function. We will not be taking the derivative of the perimeter function. So what's the perimeter of this thing? Perimeter is, so x on this side, then we have 2 semicircles. And so surface area, or perimeter and circumference are the same thing. Circumference is just perimeter for a circle. So what's the circumference of a circle? 2 pi r. Well, it's a semicircle, so half of that, so just pi r, but then we have two of them, so it'd be 2 pi r. So we have 2x's, 2x plus 2, that's an ugly looking 2, so we do that, plus 2 pi r. And so these are so tricky because, yeah, you kind of have to be careful with your perimeter equation and your area equation, your surface area. It's easy to mess up just by setting up these equations. Once you set up the equations correctly, it's just algebra and really simple calculus after that. Okay. So the perimeter is equal to p. And so now we can just we'll solve for x because we want this in terms of x. So the area equation, area is equal to, oh, it's kind of big, area is equal to, we only want the area of the rectangle, remember? So it would be x times 2r. 2r, x, that's the area. Okay. And so what we're going to do is we have two variables over here, x and r. And we want them both in terms of p. So I think what the game plan is to get either x in terms of r or r in terms of x. Plug that into area. Take the derivative, and then find r in terms of p. And plug that back into the equation, and then find a in terms of p. It's kind of confusing, but bear with me. We'll solve it together. Okay. So here we're just gonna. It doesn't really matter which one you do, since area has both r and x. This last question, circumference only had r. This one has r and x, so it doesn't matter which one you solve for now. We're just gonna solve for x. X is equal to p minus 2 pi r all over 2. And this p isn't perimeter. P is just the little p, which is equal to perimeter. The perimeter is always p. Now we have x. So let's plug this into our area function. Now everything is in terms of r. 2r. R and p, which is okay because p is a known value and r is our variable. So we're going to have to get rid of r soon. So now the 2's canceled. Nice. Area equals, we'll just multiply everything out. Rp minus 2 pi r squared. Okay. Now let's go ahead and take the derivative with respect to r. Derivative of rp is just going to be p. Derivative of 2 pi r squared is it's going to be 4 pi r. Okay. Now, since this is an optimization problem, your derivatives are optimized, or your function is optimized when the derivative is 0. So we're just going to set this equal to 0. P minus 4r squared. And if you look, we can just solve for p. Add 4 pi r over, and p is equal to 4 pi r. And then we'll divide by 4 pi. We don't care what p is. We already know what p is. It's given. Then r is equal to p 4 pi. And so we have x in terms of p and r in terms of p. So now we can just plug this back into our equation right here. This one, because this one only has r's and p's, and so we can get rid of all the r's and replace them with the p's. So area is equal to r, which can be replaced with p 4 pi times p minus 2 pi r squared. p over 4 pi squared. Okay, and so now we finally have area in terms of p, which is what we want. We can do some simplification here. So we're gonna get p squared over 4 pi minus, so you're gonna get 16 pi squared at the bottom. You can cancel that with a 2 on top and one of the pi's. So you're gonna get stuck with p squared over 16 oops, that is a 16 out of 10. Okay. And then you, oh, whoops, I made an algebra error. So you would get 16 pi squared at the bottom, and then 2 would cancel out the 16, and it would reduce it to 8 pi. And our area will be equal, and now we can write A in terms of P. Now if we multiply this one by 2, we'll get P squared over 8 pi. Feet. We wanted area, so that's feet squared, and that's A in terms of P. And that's your answer. So remember, so this one was actually a little bit different because you had to plug in, you had to re-plug in values into the same equation multiple times. And you had to get x in terms of r, and then you had to get r in terms of p over here. So sometimes there's multiple steps in reducing these equations, and then you still have to take the derivative, and the derivative is what got you the relationship r equals p over 4 pi. Yeah, so for these, just remember to be really careful when you're writing your formulas, your equations down. If you mess up the equation, you're going to mess up the whole problem. If you get your equation right, even if you make an algebraic mistake, you're going to get the majority of the points on your exam or homework or whatever it is you're doing. Okay, guys, that's going to wrap this one up. Thanks so much for watching. Good luck on all your tests and exams. See you next time.